right, thank you to the organizers for putting together this really great workshop. I feel like I'm learning a lot in these few days. And also thank you, Ferdinand, for the introduction to ions, so I can speed a little bit through that section. And I also want to point out the work that I'll talk about today was in close collaboration with Michael Gullins, who's also here. So if you have more theory-directed questions, he's here for that. So I'll be talking about the experiment that we did in which we observed the phases of one of these measurement-induced purification transitions. And the work that I'll talk about was done at University of Maryland, but the system has since been moved down to the new Duke Quantum Center. And the system that I'm talking about is a quantum computer based on trapped ions. And in our architecture, we trap these long chains of ions, so our qubits are in a single chain. And our ions are ytterbium-171. Okay, so we're familiar with this picture by now, right? We're interested in this question of when I have a many-body quantum system, I have unitary dynamics, but there are measurements interspersed. What wins? Does the quantum information survive these types of dynamics? And again, I can kind of quickly go through this thanks to the earlier talks in this. But we're basically interested in observing, can we see the coding phase where we have low measurement rate and information is protected versus the failure phase where the measurement rate is high. And so there are, of course, lots of reasons we're interested in these. And again, I'm thankful that I don't have to motivate this to this crowd. But maybe a motivation on how and why we did what we did. So this is a recent result that's been highlighted yesterday from the group at Caltech, where they looked at one of these transitions on an IBM machine. And so I've highlighted one sentence from that paper here that caught my attention, that the experiment spanned 5,200 hardware device hours, making them the most resource-intensive quantum simulations on near-term hardware. So these types of transitions are really hard to observe. They require averaging over many, many circuits, system sizes that are large enough to avoid finite size effects, and long measurement times in order to see the long time behavior that you're interested in. So in this example, this was really a brute force way of doing it. And so what I'll highlight today is kind of the way that we arrived at looking at this transition. And more broadly speaking, coming from the Monroe group and these systems that we have, we're able to really access these near-term applications on our devices. And I'll kind of highlight the ways in which we arrive at that. And so I'll talk about these along the way, but just to highlight a couple now, one of the really important ones is this idea of co-design. I think this has become kind of a buzzword lately, but this is one that I can really get behind. It really changes kind of the idea to result track. It makes it much faster, and it just makes sense. You should design your application to fit your hardware. And so I'll talk more about that. And then, of course, I think there are many reasons why we should be doing these types of experiments, even though you can just simulate these on your laptop. For many reasons, just to highlight a few, we do learn about the noise in our system beyond something like randomized benchmarking. I would say we learn the most about our system when we actually do these applications. And from the theory side, you can find working through this co-design and making it robust, efficient, really forces you to find that minimal model that works, but you can still see the critical phenomena. So it kind of pushes the theory in that way. And then on our side, I'll talk about how this type of really difficult simulation forces us on the hardware side to also advance to a place where we can do them. And if we don't even try and do these applications, are people really going to be excited? So I like to think that this also helps with that. Okay, so this is our now famous quantum computer with our screwdrivers ready for action. If you've seen the report, you'll get the joke. Okay, and it is a black box. And we like it that way. It keeps it thermally stable, any stray light from getting in or out. So this is how we like to have it operating. And building a machine at this scale has really required not only a foundation in the physics, really understanding exactly what's going on in every aspect of this system, but also kind of the overarching view of the systems engineering approach, where you can no longer look at this as a simple tabletop AMO experiment. It's really a system. So at the heart, we have our qubits, which are what we call atomic clock qubits in ytterbium-171. It's in the ground state hyperfine manifold. T1 is essentially infinite, and T2 times have been achieved over an hour in ytterbium. In our case, with microwaves, we can have about 4 seconds, and this is in a chain of 15 ions. So this is kind of at scale. Our T2 is still very long. And as I mentioned, we trap long single chains of our ions. So, and you'll see that they are actually equally spaced in this picture. So usually when you pack your ions into our harmonic potential, you have some unequal spacing. They get closer together towards the middle. But due to the fact that we're using these traps made by Sandia National Laboratories, these have 100 electrodes on them, we're able to very precisely control the potential above the surface, so that we can relax with the x to the fourth term and kind of equally space those ions. And this will become important in the way our system is constructed. Our detection is done using fluorescence detection. So we have this S to B transition at 369. So the ion appears bright in the 1 state and dark in the 0. And so we're able to threshold on a single photon when we read out for maybe less than 200 microseconds. And we image the ions onto this fiber array. So there are 32 fiber cores in this array, and they're equally spaced array. And so now we have our equally spaced chain that we then image onto that array of waveguides. And so each ion can have its own detector, and this really minimizes our detection crosstalk. Our qubit manipulation is done with a Raman transition. So we have this 2-photon process that allows us to do all of our coherent manipulation, all of our gates. And this is done with a pulsed laser at 355 nanometers. And this is a laser you can sort of buy off the shelf, and then we modify it so that we can control the repetition rate. And this allows us to have very, very good control of our coherent operations. The next element that benefits from this control over the ion spacing is the way we do our individual addressing. So in this system, we need our 2 Raman beams. So the first one is this global beam that addresses the entire chain. And then each ion also gets its own individual beam that's controlled by a channel of this 32-channel AOM. And so that you can think of it like each ion is kind of sitting in its own beam. And this system allows us complete amplitude, phase, and frequency control of each beam individually. And this is a place where we really benefited from working with L3Harris Corporation. So they have a team of photonics and optics experts that design this Raman system. This is their AOM. So this is somewhere where this is the crucial part of our system. So we're going to have the experts build it. And so we benefit from their expertise for this addressing. Our 2-qubit gates are done using a spin-dependent force, which actually excites the motion of the chain. So all the ions share these motional modes together through their Coulomb interaction. We can choose any 2 ions and turn on their beams to create a gate. And we excite the motion and shape the pulse that we apply in a way that at the end of the gate, all of the motion is out of the equation, and we're left with a spin-spin interaction. And even as we scale up the number of ions in this chain, we can continue to do this with high fidelity, just by doing this kind of pulse shaping. And then the last aspect of the machine that I'll highlight is this kind of, again, this like systems approach to this experiment. So we integrated a lot of automatic control over the last couple of years. And so in this example, we're loading a chain of ions. So you just say how many qubits you'd like, hit the go button, and then it will load exactly that number. And it does that by loading in one corner of the trap over here, and then shuttling the ion into the logic region where we have our beams. And we do all of this through Python-based control with Arctic, which has become very popular in the ion community. So we have lots of resources and ways to pull together to make that work nicely. And then, of course, we have our industry partners for those really crucial aspects of the system that make it run smoothly. So putting it all together, this is kind of what our typical performance was like at the time when we took this data that I'll present. So our number of qubits is 13 with all-to-all connectivity in the chain. Our 2-qubit gate fidelity is about 99%, and our single qubit gate over 99.9. And then we have some small spam errors. Okay, so this is going to be the system that we use in order to study this phase transition. So now jump into the particular model that we're going to study. So in this case, we have all-to-all connected Clifford circuit. So I have space, and these are the qubits in this direction, and time happening here. And we have our random unitaries with interspersed measurements. And then at each time step, we measure a qubit with probability p. And this rate of measurement is something we can tune. And in our case, the observable that we're going to use is the entropy of the system conditioned on the measurement record. And we're going to be looking for a purification transition, which means we're going to start in a mixed state, and then at the end, look at the entropy and ask, has the system purified? So this is kind of the basics of the model. And of course, now we have to turn this into something that is good for running on our system. Okay, so the first thing to do is replace those random unitaries with random XXs on any pair of ions. And so now this is our system of ion qubits. We do some kind of scrambling so that we can start in a mixed state, and then this is the beginning of the evolution. The next thing that we do, thanks to the insight of our collaborators, Michael Gollins and David Hughes, is instead of having to measure the entropy of the entire system, we really only need to have a reference qubit that's initially entangled with a system qubit. That then at the end, we measure the entropy of that reference conditioned on the measurement record, and this is enough information for us to be able to see this transition. And so for us, this is a very efficient observable. To measure the entropy of single qubit, a full state tomography, that's 3 measurements, as opposed to the full system growing exponentially. So this was very important. The next thing that we do in our system, at the time, we did not have mid-circuit measurements. So we're just keeping this chain all together, and we measure by shining the beam on the whole chain. But we do have some extra qubits, so we're going to use those as ancilla and just defer the measurements to the end. And then finally, we add one more piece. Since the circuits that we're looking at are Clifford, we can simulate them, figure out when the reference qubit is going to be in a pure state and what basis it's in. And then we can add this feedback circuit that's a kind of a quantum feedback to rotate the reference qubit into the Z basis. So then we don't even need to do full state tomography anymore. We really just need to measure 0 or 1. So this is going to amount to the entropy of a classical bit flip. Yeah?
Why can't you measure individually? I think you have your optical tracing with the fiber outputs. It would just require the resonance instead of the Raman.
So we don't have like 369 beams that only touch one ion at a time, and then on top of that, it would scatter to its neighbor. Yeah, so I guess we would need. Oh. That would be optically very complicated. I don't think, because we're focusing these 355 down to less than a micron. So it's very well tuned for 355. So even 370, I think it would just make a mess. So that's what we are doing now. So we can actually split the chain, much like the architecture that you described, and hide some ions away. But in this particular case, we just weren't there yet. Yeah. I'll take another. Yeah. Mm-hmm. Yes. Well, it's maybe a it's a quantum feedback. It's feeding back on our classical simulation of the circuit, not on our quantum activities. So these are Cliffords. We can simulate it. We know what's going to happen or what's supposed to happen, and so we can correct for that and turn it into a classical bit flip. Only at the end. For the pure circuits, yes. We know which ones are going to purify. Yes. Okay. Okay, so for the first test, we actually do look at the entropy of the reference qubit in its entirety. And we do this for 2 sample circuits just to show that we can really tell the difference between, at the end of this time evolution, this particular example, the reference qubit is mixed and the entropy is high. And then in this example, it's actually purified at this time step. And so the entropy is low. So we're not exactly at 0. Noise, of course, adds entropy. And so there is some residual amount here. But clearly, we can tell the difference. So we have a nice observable. And then in the end, what we actually do is set a threshold between these values and assign according to that threshold in the same way we do our detection of the ion. Okay, so there's one other sort of trick that we play that comes into this aspect of co-design. So and in our dynamics here, we can have measurements that are in the z basis as usual, but we could also do measurements in the x basis. And if you remember, our interaction entangling gate is an XX. And so this, of course, whether we measure in x or z, determines kind of the subsequent dynamics and how the XXs affect that qubit. And so in that way, instead of tuning across the measurement rate, we can fix the measurement rate and instead tune the probability that that measurement is in the x basis. And so in this way, we can tune across the phase transition from the coding phase where we measure very little in x, and then the failure phase where we measure often in the x basis. And what this does is we can fix at a low measurement rate, and now we've constrained the number of measurements required, even if we go for a longer time, to some small amount. But because we can tune this basis, we can still see the transition. So what this means is we don't need that many ancilla. Okay, so then these are simulations of the time evolution in the 2 different phases. So we see in the coding phase, the entropy stays high, whereas in the failure phase, we have this exponential decay. And then this is for like a single system size of 32, but we can also look at this for other system sizes. And so what you'll see is that if we zoom in on one particular time step, in the failure phase, the entropy is decreasing as the system size increases. However, in the coding phase, the entropy is increasing with system size. And so this is kind of a qualitative trend that we can look for. So it's a nice, robust observable. It's also efficient in the number of gates because we can choose, again, a small number. This is measured in number of gates scaled by the system size. So we can keep this number small and still see evidence of these phases. So again, a smart choice made there. Okay, and so our experimental parameters in the end, we looked at system sizes of 4, 6, and 8. and up to 3 measurements with our 3 ancilla. And for each point on the phase diagram, we sample up to 300 circuits, and we measure this classical entropy of the reference qubit. And these are the results. So I'm plotting this classical entropy that's been thresholded according to this separation of the 2 results that we saw before. And the simulation are kind of behind the experimental data points here. But you see we have this decreasing entropy in the failure phase and increasing in the coding phase as we increase the system size. And then we also looked near the critical regime. And so this shows that we can qualitatively see the different behavior in the phases. And taking this, getting this plot, each of these experimental points required 300 circuits, 100 in the case of this near critical regime. And so this really pushed us to get to this full stack development where we could just load up make sure the machine's ready to go, load up some circuits, schedule some calibrations, get some sleep, come back, and find the data done. So when you're looking at over 1,000 circuits, this really becomes necessary that you're not sitting there clicking every single one anymore. So that was great for us because this encouraged us to really get to that point, and now, of course, we can use this for other applications. Okay. So in talking about this result, I hope I've highlighted most of these points. So these really kind of apply to any time we're thinking about these types of applications on our NISC computers. So really thinking about this idea of co-design, how can we take advantage of the hardware that we have, and finding protocols and observables that are robust and also efficient. Okay, so then what can we do next? Well, in terms of looking at this transition, we'd really like to see the critical behavior. And so we presented a way you could do that that requires only up to 32 qubits in the system. And where we have this exponential decay in the failure phase, and if we look at the decay parameter here versus system size, as we tune this measurement in the X spaces, we see the critical point. And so this is 32 qubits, which is what our system was actually designed for with our 32 beams and 32 detectors. And so this is really not a crazy reach in the near future, but it will require mid-circuit measurement. Thank you. And so that's something that, like I said, we've done for other applications. So it's a matter of incorporating it into these larger system sizes and potentially looking theoretically at kind of what other observables can we look at. And so I'll also just mention one of the next upgrades that will allow a lot of these, kind of going to bigger system size and the mid-circuit measurements, is adding sympathetic cooling to our system. Basically what we have is this long chain, and over time, as Ferdinand mentioned before, it heats up, and so the ions are really moving axially. And so we need to cool it back down. And so by adding another ion species, we can cool without affecting our qubit. And so we've shown kind of the operation of this in a chain of 15 ions where we have some coolants interspersed, and we show we can cool in a couple of milliseconds. So then we'll have to intersperse this within our gates. And this is what that looks like. So it's kind of hinting at this of what I talked about earlier, where we can do mid-circuit measurement we have our chain, and it's in the zone with the beams here, and then we can split it into pieces, and then we read out part of the chain while the other stays protected far away. And so we've shown this there's a paper on the archive on interactive protocols that has the demonstration of this. So this allows us to do that mid-circuit measurement, and this will require some recooling after we then merge the chain back, so kind of that sympathetic cooling comes back into play again. So as I mentioned, the system that I've been talking about, this work was done at University of Maryland, but we've since moved down to the Duke Quantum Center. So this is our first team photo from this spring. We're growing very quickly, and we've got lots of great faculty down at Duke working in quantum, not just in ions, despite what you might see on here. So yeah, we're excited that we're in this new center together, and it's really quite an exciting time to be at Duke and to be working on these systems. I also want to mention that I'm part of the construction team for the next generation system, which improves on the previous one in several different ways. So we're looking forward to that coming online hopefully this fall. We've just trapped in the last month, so kind of getting started with tuning that up. Also mentioned briefly, a little self-promotion, I'm starting my own lab and looking at kind of these scalability challenges and materials and devices and how we can advance the ion trap technology into the future. So if you're interested, just contact me directly. And so finally, let me just say thank you to the experimental team. This is actually just the team members who worked on this particular project. There are even more mentioned down here that kind of keep these systems running. And then, of course, our theory collaborators work closely with Pradeep, a grad student who's with Michael Wellens at University of Maryland. So thank you.